be presenting my work on reinforcement learning based variable horizon MPC for multi-robot system. So particularly there are three keywords over here. One is the system that is we are we would be talking about multi-robot system. Another part is variable horizon model predictive control. And then third is how it is RL based. What is the role of RL in VHMPC for multi-robot systems? So starting with multi-robot system. So primarily the work I have done is not constrained to any particular model or particular type of system. It is in general applicable to any multi-robot system, say aerial robots or underwater robots or ground robots. But the experiments which I have done uh, has been done on mobile robots. So that is why in introduction I have talked about uh, the introduction of mobile robots in industry, which was first done in 1950s, where Barrett launched AGV, which is nothing but a automated guided vehicle. So instead of car-like robots, which we see today in our labs, maybe tank type or Ackerman type or mechanism wheels or differential drive robots, initially it was automated guided vehicle. That is, it was a train-like system guided by a track whose image is shown in figure 1. This where this is kind of engine of a train and these are bogies, which was particularly used for transportation purposes inside a warehouse or a factory. But what a mobile robot means, a mobile robot basically means anything which can move from place A to place B. Inherently, what purpose they solve? The most beneficial advantage of a mobile robot is it does nothing on its own self, but it can be integrated with a lot of tools. It can be integrated with a lot of sensors, other hardwares. For example, in video number 1 and 2, in video number 1, you can see two manipulator arms are mounted over mobile robot and they are coordinatedly performing a payload transfer operation from different positions. In video number 2, you can see multi-robot systems are working in collaboration with a human to put a pipe inside the designated holes. Now, again, you can see mechanism wheel-based mobile robots, uh, which uh, parallel robot is mounted on all three of those. So basically, mobile robots can help us to say carry different kinds of payload, different kind of sensors, and the application of these multi-robot system varies from heavy payload transportation to construction sites, even planetary exploration. Say Mars rover is one single rover, but then the helicopter is flying with it. So basically, they are working in tandem to collect data in biomedical assistance or in surveillance and inspection. We have also seen recently the war broke down between India and Pakistan, and the use of drones or kamikaze drones. Now it is a talk of the town that everybody knows that how these multi-robot system works. Another application recently which we have seen by Bot Lab Dynamics Delhi, which is getting very popular in India, that is the drone shows basically for maybe advertisement or entertainment. Uh, so now to control a multi-robot system, a very powerful controller is required. And predictive control is one of the popular traditional control used to control multi-robot system. And this is because it has certain advantages over other controllers. So here I have listed down few of the advantages. That is, it can handle multi-input, multi-output system. And multi-robot system is basically a multi-input, multi-output system where the control inputs of one robots are also dependent on the positions and the states of other robots as well. Predictive control has another advantage of handling constraints beautifully. One inherent constraint which we need to put when we are working with multi-robot system is obviously collision avoidance. And model predictive or basically predictive control can handle constraints very well in comparison to different traditionally control methods. Also, predictive control, as the name suggests, has a preview capability. I would explain it later in the presentation that what it means to have a preview capability. Basically, it can look into future and then decide what is best for itself. Now, one of the most famous predictive controller is model predictive control, known as MPC. It came into being in 1960s, 70s, and it was initially introduced into chemical industries or process industries, but it has been used in robotics very widely since 2000s. And to name a few, the Mars rover uses model predictive control. Initial robots of Boston Dynamics used model predictive control. Also, Altros robot, if I'm naming currently, a home robot developed by Amazon Robotics uses model predictive control. So before basically RL came into powerful being of controlling robots, model predictive control was the first and best choice of roboticist engineers, and it still holds its ground. So here I have listed what are the basic components of model predictive control. To implement a controller, you basically need a model, which basically gives you the mathematics of your robot. So here I have listed out a linear model, basically xk plus 1 equal to xk plus b uk, where x encapsulate the states and u is the control input. Second component of model predictive control is the cost function. And see, now the cost function and the constraints, which I feel is the best thing about model predictive control, because it can be easily and comprehensively developed and designed, which is say easier or than comparison to other controllers. For example, if I explain you the first term of the cost function, that is x minus x desired transpose q x minus x desired. It is nothing but it is an attraction force towards a desired position uh, where we would like to send a robot to. It can be a set point control, or it can be the desired position can also come from a design trajectory. The second term, u transpose ru, can be also read as u minus 0 transpose ru. So it is nothing but it is saying that my control input should be as close to 0 as possible. That is, it is saying the control effort should be as less as possible. Again, then there is another term, delta U transpose as delta U, where it says that the difference between two consecutive control inputs should not be much higher. It should be as less as possible. For example, if you are having a 90-degree turn, at the last moment, you can change your steering angle, which may be a control input from 0 degree to 90 degree. But that is not comfortable to the passenger sitting in a car. So we would like to change from 0 degree to 90 degree in incremental steps. That basically what third term delta U transpose as delta U does. And similarly, so on. So basically, you can design a term in the cost function as per your requirement, and which makes using model predictive control very intuitive and comprehensive. Similarly, different constraints can be included easily into the model predictive control framework. And what it does after getting all these information of model, cost function, and constraints, basically it solves the optimization problem. And the length of the optimization problem basically varies based on a term which is known as prediction horizon. So you can see the cost function is summed over L equal to 0 to n minus 1, where n is nothing but the prediction horizon, which tells what is the length of the vectors that MPC is going to optimize the future trajectory over. To understand it more deeply, let me explain how the progression of MPC goes on. Imagine you are playing chess with your opponent. Now your opponent takes a turn and places some piece of the chessboard to some place. Now what you do? You perceive the environment and then you take your future action. Basically, first you plan in head. In your brain, you first predict that if I take this step, then the opponent may take this step, and then how this progression is going to be in future. So basically in MPC, standing at time step k, it predicts in future that if this is the control input, how my trajectory is going to be. But it does not implement all of those. Like in chess, you think, say, 5, 6 steps in future that this is going to be my strategy for next 4, 5 steps. But that is not exactly what you implement. You take just one step at a time. And then at the next step, after the opponent's play, again you do the same exercise in your brain of predicting or analyzing what may happen 5, 6 steps into the future. This is exactly what MPC does. So standing at time step K, it solves the optimization problem for a length of future steps, which is known as prediction horizon. And then it only implements the current step control input. So it moves one step and then again it solves next n control inputs, then implement just one control input and discards all other control inputs. So this is how the progression of MPC goes on. So which basically tells that uh, n, the value of prediction horizon, determines how far we are looking into the future, uh, right? So now prediction horizon. Now I would like to deeply discuss how the value of prediction horizon affects our control performance. So here I have declared that prediction horizon is a gift and the curse. I would like to take an analogy here. Suppose you are traveling from Jodhpur to Delhi by road. Now you would like to plan your journey that uh, what is the distance between Delhi and Jodhpur? Okay, it is this number of kilometers. Now, okay, I would leave at this point of time so that there is less traffic or some other things. You would like to optimize your journey as much as possible. With the limited information you have, with the limited information from the Google Maps or someone who has traveled from Jodhpur to Delhi before you. But assume if you have a Divdrashti, if you can see future, or if you have, say, this magical vision where you can see the complete highway, complete road from Jodhpur to Delhi. If you could do that, you can pinpointedly decide, okay, the highway is closed here. I have to take this reroute. I will take a stoppage at this particular petrol pump or say subway station to drink or go to washroom. And here the traffic at this particular time is higher, so I will not cross from this street. You could plan it to the maximum level, and your journey from Jodhpur to Delhi would be the most optimal in whatever say how you define your optimal journey, whether in time or whether in comfort level or whatever. Now this all came with the assumption of having a Divyadrashti, that you have the magical power of looking over the full highway from Jodhpur to Delhi. Which basically means what? That you have a very, very, very huge prediction horizon, that you can look into future as much as possible. But also processing all that data requires a lot of computation power. It is not easy to process all that data starting from Jodhpur to Delhi. What this concludes to is that having a longer prediction horizon improves the performance of the controller, but also it becomes computationally very expensive. And that is why it is required to have a balance between computation and performance. And hence, it is very important to smartly choose your prediction horizon value. Now, the problem is that a single prediction horizon value cannot be said optimal. You cannot say that the value of prediction horizon equal to 25 is optimal. No, it depends on the task you are doing. And it is more difficult to tune the value of prediction horizon when you are working with multi-robot system. It may be easier to tune the value of prediction horizon when you are working with single robots. But in multi-robot system, if you change the orientation, if you change the initial positions of the robots, if you change the task, the optimal value of prediction horizon changes. By optimal, I mean, again, whatever your cost function is, whatever value of prediction horizon which fetches you the least cost in the given computation resources. And to deal with this, researchers came up with something known as variable horizon model predictive control. So they said that instead of having a fixed prediction horizon for the whole of the task, let's use a version of MPC where the value of prediction horizon is variable over the task. For example, a very basic version of VHMPC can be, say, for example, I start with a very high value of prediction horizon for, say, 50. And then my proposition is, as I move closer to my goal, I no longer need to look much into the future. And so I can decrease the value of the prediction horizon by 1 each time. So at initial step, at 0th step, say my value of prediction horizon is 50. At next step, it can be 49. At next step, it can be 48, and so on. The problem with this is, suppose your experiment required many more steps than the maximum value of the prediction horizon. Say, if you started with a maximum value of prediction horizon of 50, but your task required 200 steps, then at 51st step, your prediction horizon has been reduced to 1. Now, if it has been reduced to 1, it does not encapsulate the advantage of MPC. The controller is now nothing more than a PID controller. So what is the advantage of using MPC then? Then the researcher suggested, okay, then we will not reduce it continuously. What we will do, if we reduce it by 1, but we will stop reducing it once it encounters some obstacles or something, and then reduce it again. Another option was, okay, I will reduce it by 1, but it encounters something, some obstacles or some inaccuracies or some perturbations. I will again increase it by 1 and then reduce it by 1 only when the things are normal for the controller. But all these scenarios were actually not very good when working with multi-robot system. And also there were some advanced version of VHMPC where some functions were developed to decide the value of prediction horizon. Some people have also included inside the objective function of the model predictive control. But all these methods were task specific or worked only for a certain category of systems. And this motivated to actually develop a system uh, or use some learning based technique to decide the optimal value of prediction horizon for each of the robot in a multi-robot setting. This is the overall framework of reinforcement learning based variable horizon model predictive control for multi-robot system. Here, I have used a collective RL agent where it takes the global reward value and the states of the robot, where the states of the robot basically include the positions of all the robots, and it gives out an action which is then used to calculate the optimal value of prediction horizon for each of the robot. So the value of prediction horizon is not only variable in time, but also it is different for all of the robots at each time step. Then this, once we receive the value of the prediction horizon, it is then used by the optimal control problem uh, to solve the control inputs of the robot. And then those control inputs are communicated to the multi-robot system, which then propagate to next state. And this loop continues. So here I have mentioned that I have used a collective RL agent. So I would like to define what I mean by collective RL agent, or basically collective learning and individual learning. So individual learning would be something if, say, I train my policy on a single robot and then clone it on all other robots, which is shown by the first block diagram, where the RL agent uses the states of a single robot and learns the policy, which gives the prediction horizon of that robot. And then we can clone that particular policy for n number of robots. This is what we call individual learning. And Then we have collective learning. So in this particular case, I have used collective learning, where the RL agent is trained by using the data from multiple robots. So the state basically encapsulate the position of n number of robots, and then a single policy is learned which gives out the prediction horizon of all the robots. The advantage of this we will see in the results I would define. Now, this work which I am talking about is already published, so I am skipping the mathematical details from this presentation. I am mostly talking about the philosophy of the work. But if you would like to read the mathematics and the reward function design, you can basically refer to this particular paper, which was published in ASME Journal of Dynamic System Measurement and Control, and it is titled as Reinforcement Learning Based Variable Horizon Model Predictive Control of Multi-Robot System in Dynamic Environments. So here I would now discuss the results of this particular framework. Initially, I would start with the ablation story of a single robot moving in the presence of 15 static and 30 dynamic obstacles. You see then the dashed lines are dynamic obstacles, the black discs are static obstacles, and you see a single robot moving from 0, 0 to 30, 30. And on the right hand side, you have seen the prediction horizon propagation. So the prediction horizon value varies between 0 and 50. I've kept a maximum cap of nmax equal to 50. Which has been also experimentally verified, as well as in the literature. I found that very few robotic application use a prediction horizon greater than 50, maximally use between 0 and 50, or we say 1 and 50. The prediction horizon value is a natural number, it cannot be 0. So in this particular case, when I compared it with, say, fixed horizon cases, fixed horizon MPC. Here we see fixed horizon value of 1 basically could not solve the task, hence it is colored with red. And then we see the number of iterations, say 50 was the fastest, and RL was the second fastest, close to say 50 in the number of iterations. But when we see the computation time, if you see the computation time, basically the blue bars, you see that RL is almost 3 times faster than a fixed horizon 50. So though the number of iterations are same, but the computation time required is much, much less in comparison to the best fixed horizon. Next, we move to multi-robot system, and then we see an interesting result over here. See, you see two plots over here. Two robots are trying to do a diagonal position exchange task, and this is deliberately done in a way so that they meet at a midpoint and there is some collision situations. Now, the best performing fixed horizon was fixed horizon 30, and you see it takes a longer path. It takes a longer path. Basically, they approach the midpoint, and then in order to avoid the collision, they move parallelly and then they cross each other. So it takes a longer path. While in RLVHMPC, you see it takes a shorter path, both the robots, the red and the blue, robot 1 and 2. Why does it happen? To understand this, let's look at the control inputs of both the robots. Now, in case of fixed horizon 30, here I've zoomed in the control inputs. The velocity of y direction of one robot and the velocity in x direction of another robot is actually identical. They are overlapping. And that makes them to reach at the midpoint at the same time, and which arises a collision avoidance situation. While in case of, is my camera on? Sorry, then just a minute. So I was explaining in the first case, you see that the velocities, the y direction velocity of this robot and the x direction velocity of this robot is actually identical, and this makes them reach the midpoint at the same time, and which arises in a collision situation which they have to avoid. And in order to avoid the collision, they move parallelly and take a longer path. But in the RL case, you see that the velocities are not identical. Now, it is important to note here that the robots are not actually being controlled by RL. They are actually being controlled, or their velocity is being generated by MPC. But RL learned to manipulate the value of prediction horizon in such a way that it made one robot slower and one robot faster so that they do not reach the midpoint at the same time. RL always surprises you. Say you plan it to do something, but it might do something more than planned. So in this particular case, RL smartly manipulated the value of the prediction horizon to make one robot faster and one robot slower, so that they do not actually get into the tussle of avoiding collision, and hence the path in the case of RL is shorter in comparison to best performing fixed horizon MPC. Next, we move on to control of multiple robots. Here you see three different tasks. One is square formation, another is parallel line formation, and then third one is triangle formation. So in all these cases, 20 robots were used in presence of two static obstacles. And believe me, these methods were not trained differently. Only a single policy was trained on some task of 20 robots. So this is also shows that this method is generalizable over a variety of tasks. It is not like that if it is trained on a square robot task, it will just solve the square robot task. If once trained a policy for 20 robots, it can be implemented on any task of that particular number of robots, which was lacking in the previous RLVH MPC methods. And this table shows the number of iterations taken by different fixed horizon value in RL for these methods. We also implemented this strategy on hardware. So here I'm showing one of the case. You can again refer to the paper for various other results, ablation studies and everything. Discussions are provided on how increasing the number of obstacles basically affects the RL agent, and other interesting results which can be read in the paper. So here I'm showing one of the hardware experiment. The task was for the robots to navigate into a star formation, like how we draw a star in a paper. So here you see 5 turtlebot robots moving such a way that they form a star-shaped trajectory using RL-based variable horizon model predictive control. And also another contribution of that paper was VODCA, variable versatile on-demand collision avoidance method, which I have skipped for this presentation because it has nothing to do with RL. But still, it can be referred in the paper if you would like to. So this is how they completed the task. Now to have a deeper look on how VODCA or VODCA works, the collision avoidance method. If you would like to have a close-up, that it manipulates the position in a bit so that it does not collide with other robots. So basically, the key takeaways of this presentation is that the prediction horizon uh, is the smart choice of prediction horizon is very much required for the performance of the model predictive control for multi-robot system. And the prediction horizon value basically determines a balance between your computation and your performance. And since the previous methods were not generalizable enough, we have to think of a learning-based method which can be generalized over a variety of tasks. And for that, we have used a collective learning framework uh, to learn the optimal value of prediction horizon, which is variable over time and within the number of robots. Also, VODCA, that is versatile on-demand collision avoidance, was another contribution of this work. So with this, I end my talk. Thank you very much, and I would like to address any questions if you have. Okay, fine. So the obstacle information is not given to the RL. The RL only receives the position of all the robots. The collision avoidance part is taken care by MPC. So it is developed as a constraints and then included into the model predictive control. So it is also interesting that in the collective framework, collective RL framework, now the prediction horizon of say jth robot is also affected by the positions of the ith robot. So the prediction horizon value is not only affected by its own position, but the position of all other robots. But the obstacle positions are not given to the RL agent. It is taken care purely by model predictive control. I hope I was able to answer your query. Okay, then I would like to conclude today's session. I would request all the attendees today if they would like to present their work in the next talk, or they know someone who would be eager to present their work with the reward loop community. Please share this message with them. Thank you all. See you in the next talk.